Okay, so how is everyone today?
Good.
Good? All right. Okay. Are we zoomed in too much? It's a little better. All right. So today's the 6th. Okay. So now, just to give you an update on like the state of the course, is that we've lectured like in here on the screen. This is like the 4th time or something. I can't remember, but a couple times. But we've been in lab twice. So now, to remind you, y'all are a population, and you have a wide amount of experience. And specifically, some of you have done programming before, and some of you this is like the first time. So if you've done programming before, up to now, the course has probably seemed to you like probably pretty straightforward, at least the programming aspect of it. And maybe the GitHub thing was a little new, maybe not. And then for some of y'all, this was like completely new, like you've never done anything like this before. Okay. So I just want to keep reminding y'all of that, so like, if you've never programmed before, and then you look over at that other student who you know, or maybe you don't know him, and then you realize, wow, they're already done? And, don't take that to heart, because what all that probably means is that that student has done programming before, okay? And similarly, vice versa. Y'all that have done programming before, and y'all see ones that are other students who are having difficulty. Don't moralize. Okay, it's because they're learning the first time. Also, hopefully, concerning me, y'all can all kind of like remember that I'm trying to play both audiences. Trying to satisfy both both audiences. I gotta kind of take y'all as y'all are. Okay, but that being said, there hasn't been any strict due dates yet, and I didn't want to have any until I had been able to demonstrate all the different mechanical bits in the lab, and now we've done that. So as a result, there are currently, at the present time, 3 programming assignments: 000, 001, and lib. Okay, they are due Tuesday, which is to say 5 days from now. And understand what that means. That means that if it appears to me that you basically haven't tried anything, when I look at your code on Tuesday, then that's it. You're not going to submit anything further. But I mean, you can, but I won't accept it, right? But after that, but supposing you have been trying, but it's not correct yet, well, that's fine as far as I'm concerned. I'll extend it as far as needs be. Okay, it took for a very generous definition of, yes, it appears to me that you're trying. Okay, so any question about the due dates? The whole point and purpose is that again, I have to sort of, it's both my like teaching philosophy and also the fact that y'all are diverse. This is the 3rd week or 4th, I don't know. It's one of the weeks, and it's a little bit concerning if you don't know something right when I want you to know it. That I'm concerned, if that's the case. But if you know it by the end, that's all that I actually care about. So if you can demonstrate to me that you know it by the end, that's all that matters. Okay. So as a result, that's why the due dates are kind of rolling as they are. Any questions about that? Okay. So let's talk about some math then. So the first thing I want to remind you of is that we've talked about what this means. Okay, and of course that means 5. Right? So no, not exactly, right? It means 5 factorial, and we've already written the definition of it, so I'll just write it here. N factorial, remember, is a function with signature naturals to naturals, which is to say that you input a natural, and then a natural is output. And what's the least natural? 0. So we need to specify what it is that we'll do with that least natural, which is to say we need to say what 0 factorial is. So what is it? It's 1. And then otherwise, which is to say if we have any other natural, If we have any other natural, then what's the formula? Right, n multiplied by n minus 1 factorial. So this definition is said to be recursive. It's called recursive because this is saying something like, therefore 5 factorial according to this is actually 5 multiplied by 4 factorial. So the fact that factorial is on both sides of this equation, that was a joke. This on both sides of this equation means that this is recursive, right? Okay. Good. So now a frequent question, and it does, when you're teaching, because since y'all are mostly, not all of you, but mostly math majors, if you end up getting a math degree, you got to understand that one way or another you're going to be a teacher of some sort. So you might be like formally a teacher, like I'm like up here teaching, and then lots of people who get math degrees, they teach like high school and stuff like that. But lots of other math degrees, they end up doing something else technical, but it's not teaching. But in the end, you're going to have to be helping people with math. Okay, so I want to make sure that you understand that there's a couple rules about teaching. Okay, especially something like math. So one of them is that the stuff that you say needs to be correct. Obviously, it's no help if it's not correct. So that's like the first rule. The second rule is that it's a good idea to repeat yourself, and that's a good idea. The third rule is that it's a good idea to repeat yourself. So to repeat, why 1? It's the multiplicative identity. Okay, factorial. In factorial, what it is that you take a natural, say like 10, and what you do is you take all the naturals, all the positive naturals, okay, up to and including 10. So you take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you combine them all into a single natural by multiplying them all together. Okay, so then 10 factorial is a product with 10 factors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so like 100 factorial is a product with 100 factors. So 0 factorial would mean a product with 0 factors in it, which is to say the empty product. Well, what is the empty product? It's 1, the element that is neutral with respect to product, the multiplicative identity. Okay, so multiplicative identity. So altogether, what I want you to kind of see is that this definition here, just is a lot of it's really biased toward multiplication. So to that end, I'm going to just rewrite this real quick. Except instead of calling it factorial, I'm going to call it. I'm going to give it a function name like in the usual way, and call it m for multiply, so that it looks like this. So it'll be 1 here, and then n is 1 when n is 0, and it'll be n multiplied by m of n minus 1 otherwise. Okay, so that's just factorial, but instead of calling it factorial, I'm calling it m. Now the reason why I want to do that is because right now this is what I want you to do. Is it observing that that this is for multiply. Observing that, I want you to make a function a from naturals to naturals that would be completely analogous, but for addition. Okay, so I'm gonna give you a moment to do that. All right, so in the interest of time, so we want to make the definition of A of n, and it'll again be defined by clauses, like so. So then the first clause tells you what it is that you do with the least natural. So when we do that, so for the least natural we're going to do something, and then the second clause is what we do with naturals that aren't the least natural. All right. So how about this one? I'll start with this one. How are we supposed to like take that and edit it and make it this one? Okay. So we'll have a. So this is a term with two factors, because remember that. Terms are things that are added together, and factors are things that are multiplied together. So this is a single term, two factors, the left factor and the right factor. So again, we'll have there will be two items. There will be a thing on the left and a thing on the right. So there'll be n, and there'll also be a of n minus 1. And then what are we supposed to do with them? Add them. All right. Good. So instead of multiplying them, we're adding them. Fine. And then what about this case? But I thought it says 1. Very good. So again, what this is saying, what A of n is like conceptually doing, like A of 10, that would mean something like take all of the positive naturals, or even it doesn't matter. You could even say all of them. Take all the naturals up to and including 10, and then add them all up. So then, and if you like, you could say just the positive naturals. You could view it in that way. And so then A of 0 would mean take no naturals whatsoever, and then add them all up. The empty sum. So the empty sum is 0, because 0 is the additive identity. Good. So now let's evaluate this. So, for example of doing this, so I'll make it nice and small here. So A of 3. And again, taking the convention that clauses are numbered top to bottom, starting at 1. Now, I'd like to point out a slight inconsistency that it's worth noting anyway, is that in a math class, as I said, like on the first day, when the instructor or the textbook says naturals, you need to very carefully check whether or not the instructor or textbook or what have you considers 0 to be natural, because there's some variation on that. I can't predict the future, but more or less, well, I'll say it like this: when the choice is mine, I always say that 0 has to be natural, and it seems to me that historically speaking, that's the arc where it's going. So like I would say that probably like in 50 years, no one's going to be saying that the naturals start at 1 anymore. So it really disturbs me that that these clauses start being numbered at 1. Like I really want to write 0 there, but but even though the naturals are like soon everyone's gonna say that they start at 0, I think this is going to be this way forever, because like, well, as far as I can tell, because everyone does this. Like there's like no variation. Anyway, I just wanted to point out that inconsistency to you. So to do this, if we want to evaluate A of 3, then we need to use the second clause. Now the second clause says that that this should be 3 plus A of 2. And so again, the fact that A appears on both sides of this is part of, that's a manifestation of what it means to be recursive. Okay, so then this 3 is just fine, and then this A of 2, according to the definition there, would need to be 2 plus A of 1. The 3 and the 2 are fine. And then A of 1, according to the definition, would be 1 plus a of 0. The 3 and the 2 and the 1 are fine. And then the a of 0 is what? 0, according to the definition. So again, the clauses that were used were first 2, then 2, then 2, and then 1. Okay, and then if you cared to do so, you could add that all up and get 6. So any question about this? Now, I'd like for you to observe that if we took all the pluses and changed them to multiply, and we took the additive identity and changed it to the multiplicative identity, then this would be exactly 3 factorial. Right? Okay. So this definition is like exactly the same thing as that one, but for add. Okay. So now I want to make something clear about the way so you're gonna, part of what y'all are gonna, as a consequence of us having enough labs to where I think y'all know enough to where I can start giving you a bunch of assignments and y'all not get in a cold panic. You're gonna do these kinds of things, but I want to make sure it's clear how the machine actually does this. So notably, I want you to see that there's 4 things here, 4 items here. There's 3, 2, 1, and 0, and then we've got these pluses here. And I have a question. Does it matter what order we do the adds in? What I mean to say is, like, if I wanted to do this in sort of a simple-minded machine way, is it okay for me to do that add first, or must I do that one or that one? Okay, so yes, I do agree with that, but that would mean can I move these around? Okay, but that still doesn't say which one of these do I do. So it's not the C word, it's the A word, the associative one, right? So what that means is that addition is associative, which means it's permissible that you should put parentheses anywhere you want. That's what says what order are you going to do these in. So like I could put parentheses around these, the 2 and the 1, so that would force you to do the 2 plus 1 add first. Or I could put parentheses around the 3 and the 2, and you could do that. And it doesn't matter because addition is associative. All right? Is multiplication associative? Yes. In the same kind of way that you could write like 2 times 3 times 4 is 24. And you could do that by doing 2 times 3, which is 6, and then multiply by 4 to get 24. Or, if you like, you could write, if it's 2 times 3 times 4, you could do 3 and 4, that's 12, and then multiply by 2 and get 24. It doesn't matter where you put the parentheses. But there is an associativity and parentheses issue, and I want to make it clear how the machine does this. So if you, so this is the calculation without, well, let me say it like this, making the associative, the associations explicit. So now, what explicit? So what I'm going to do is I'm going to write something, and it's going to be really overbearing. But what I want to explain is how the machine does this. So if you asked it to evaluate A of 3, then what it will do is it'll say something like, okay, well, that's got to be 3 plus A of 2. Like that. So far, so good. And then, conceptually, you might think it asks itself, do I intrinsically know what 3 means? And the answer is yes. It intrinsically knows what 3 means, but it doesn't know what A of 2 means. So it has to perform more work to determine what that could possibly mean. So as a result, what happens is that this 3 sort of can just hang out right there. and then plus, and then a group gets put right here. And in a sense, you could think of it like the machine is saying, well, I need to evaluate a of 2, so what goes in there? And the answer is that 2 plus a of 1 goes in there. Okay. And then, you know, by this time, MATLAB's not even close to thinking about that 3. That's like way on the back burner. And it looks at that 2 and says, do I know what that 2 means? And yeah, it knows what that 2 means. But it doesn't intrinsically know what a of 1 means. So it has to perform more work to figure out what could possibly be meant by a of 1. So this 3 just hangs out here. This 2 just hangs out here. And then a new group is made. And then in here, it inserts what, you know, more or less, you could think what the definition of a of 1 is. Well, what is the definition of a of 1? It's 1 plus a of 0. Okay. And then, MATLAB, you know, in a sense, MATLAB can't see the 3, can't see the 2. It's gone. It's out of consideration. It looks at the 1 and asks, do I know what that 1 means? And the answer is yes. That is something that it knows what that means. But considering that a of 0, that's not something that it intrinsically knows. So it has to perform more work to figure out what could possibly be meant by that. So you get 3 plus 2 plus 1 plus, and now a new group is added. And in there, I'm supposed to write what a of 0 is. So what's a of 0? It's 0. And then MATLAB, you know, asks itself, concerning the things that are in this latest group, do I know what 0 means? Yes. And there's no further. I don't need, you know, MATLAB doesn't need to make any further considerations. It knows what 0 means. So as a result, MATLAB knows that that 0 with parentheses around it, it's permitted that you can remove the parentheses. So I copied the same line, but just removed those parentheses, and now it, in a sense, reanalyzes that and says, 1, I know what that is, 0, I know what that is, plus, I know what that is, so that is 1. So this group is replaced by that group. And then MATLAB knows that, well, because of the associative rules, it's permitted that you can delete those parentheses around the 1. And then it reanalyzes this expression and asks, do I know what 2 is? In fact, it doesn't ask itself again because it still remembers that from the last time it asked. It does know what 2 is. And then lately, it's figured out that, oh, that was a 1 all along. So 2 plus 1, oh, that's a thing. So then you can write this. 3 plus what goes in this group? 3. And then MATLAB further knows that because of the structure of the expression, and this is addition, and addition is associative, it's permissible that we should remove those parentheses. So that it's this. And then now, here we are, essentially. So we were right here. I wrote 3, and then add, and then MATLAB had to think, what could that possibly mean? The answer to what could that possibly mean is that means 3. That's what that means. So then now these can be added to obtain, you know, there's an implied parentheses. I won't force it that far. You know, I could put an implied parentheses around all these and do one more complication, but whatever. So you look at this, isn't this like really like tedious? Yeah, no dispute. But this is in fact more or less exactly what the machine is doing. And now, you know, it's kind of surprising wow, is that what it's doing? Now, y'all are going to implement this function in MATLAB, and when you press go, you know, when you say do it, and it's right, it's like instantaneous. Okay, so like if you can imagine, like you know, hovering your finger there over the enter key, you're about to press enter. You know, then you press enter, and that little mechanism in there finally gives away as you have enough pressure, and then you finally hit the bottom of the keystroke. Okay, before you even sense that you've hit the bottom, you know, because it takes a while for the signals to travel up your nerves to get into your brain. Before that's even happened, MATLAB is finished. Okay, it's really super fast. Nevertheless, look at all the work it's doing. Okay, now this sum right here, this sum is, notice that these terms are in descending order, 3, 2, 1, 0. Is it possible to make it be such that it would be in ascending order, like 0, 1, 2, 3? How could we arrange that? Right. In that clause, we could commute that. We could commute these terms like so, and then that would cause essentially this whole mechanism to shift like that, to be like reflected. In the end, it would be 1, 2, 3, 4, but then all these parentheses over here would just sort of be over here. Okay, says it okay? Now the reason why this is what the machine actually does, and the reason why, you know, if you were to evaluate this function as a human, you'd write it like this. The reason why is in the end because you know, after long care and instruction in Miss Harris's 4th grade class, that addition commutes, right? So then humans we just don't even write the parentheses usually when they don't matter. Okay. So now here's the next thing. So to remind you, you know, if I say let n be natural, x real, like this, then we've defined two things. We've defined a variety of things, but among those is this. We said that when you multiply by a natural, that actually means repeated addition. You know, because we defined that that function mult underscore n underscore r. You know that one. And you know, this is 0 and then plus x plus dot 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 plus x, and then you're supposed to make n copies of x. So what I want you to take away from that is that multiplication by a natural, so multiply, is repeated add. You do add over and over again. Similarly, if you write x and then caret n, like that, so where caret being the punctuation for exponent. So what is caret? So multiply is repeated add. What's caret? Repeated multiply. That's what it is. So it means that you make a bunch of x's, you make n x's, but instead of adding them, what do? You multiply them. And instead of using the additive identity, you use the multiplicative identity. Okay? So what I want you to see here is that there's three operations at play. So we've got add, you know, and we're imagining that you know what that means. Like that's something that you knew before you got here. And then if you do repeated adds, then that's what multiply means. And if you do repeated multiplies, you know, imagining that that's something that you knew how to do before you got here, then that's what caret means. So that one is repeated that one, and that one is repeated that one. And so the question is that can you see that in principle there's no reason to stop? Right? If this one is repeated that one and that one is repeated that one, then surely we could make a next one that's repeated that one. Now, what is the next one? What is it? Good. Most people don't know the name. So if we do repeated this one, Now, repeated caret is somewhat uncommon. Like, it doesn't show up a lot. And as a result, there's a lot of competing notations for it. So I'm just going to use what I consider to be the most common notation. So the most common notation is an up arrow. So if we do repeated caret, the next bit of punctuation is written as an up arrow. Okay. So what I mean to say is that if you write still with n is natural and x is real, if you write x up arrow n, then that means something. What does it mean? It means you make n copies of x, just like before. So we'll do, x, x, dot, 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 x. So there's n x's right there. And it's not that we're going to combine them with add, and we're not going to combine them with multiply. What are we going to combine them with? Caret. Okay. Now, notably, I'm currently not addressing what, if anything, we should put right there. Okay. So here, when we were dealing with add, we put 0. Here, when we were dealing with multiply, we put 1. Here, I'm just leaving that open currently. So what this means, for example, to give some examples, we could say something like, if you write 2 up arrow 4, like that, what does that mean? So it's this is the thing, and that's what we're doing, and that's how many times we're doing it, in a sense. So the 2, we need to make how many copies of the 2? 4 copies of the 2. So 2, 2, 2, 2, and then what? Yeah, caret, 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 caret. Or 3 carets, I guess. Like this. Okay. So everybody got the idea? Okay. So what I want you to see is that now I'll write them all here. So 2 caret 4 would mean, again, we have 4 2's, like that. And now these are multiplies. And 2 multiply 4 like this. Now the way I wrote it up there, the natural was on the left, but I'm going to make it on the right. So this would mean, again, 2, 2, 2, 2, and these are adds. All right. So I have a question for you. So the fact that that addition is associative means that you could, for example, do this. You could say that what you mean by this is you could say that we're going to do it this way: 2, and then I'm going to insert these parentheses like that, and then that. The fact that addition is associative means that is okay. Similarly, because multiplication is associative, we could do it like this. We could say 2 times 2 times 2 times 2 like this. So you could put a group around the last ones. Now, here's my question, finally. Is up arrow associative? That would mean that it'd be fine for you to put it would be fine for you to put the parentheses anywhere you cared to put them. That's what it would mean if it were associative. Okay, so let's consider. So the question is this associative? All right. So well, concerning this, 2, 2, 2, 2, with carets in between. On the one hand, we could parenthesize it like this. I could say, well, we're going to do the last 2 like that. And then after we've done that, we're going to do this like that. So that's a complete parenthesization. because that's telling you that because of the parentheses, it is necessary that you should do that one first, etc. So this is a complete parenthesization of that expression. We must do that one first. The answer would be, so that 2 is unchanged because we can't do anything with it yet. Then we have this. That 2 is unchanged because we can't do anything with it yet. And then 2 caret 2 is what? 4. Dropping the round parentheses. So then now doing this, between these 2 carets, which one are we supposed to do first? That one, right? Because it's the one that's in parentheses. So what's 2 caret 4? 16. So this would be 2 caret 16. And then what's 2 caret 16? Very good. 6, 5, 5, 3, 6. That's a number that it's probably in your interest to memorize. You know, if you can. The powers of 2 is important. So that's that. Now, if up arrow is associative, what would that mean that I could do if it were associative? Yeah, I could put parentheses in a different way. So essentially, I took this expression and I said that the way, you know, like I put the parentheses such that we would do that one, and then that one, and then that one. So that these parentheses cause us to do them right to left. So now I'm going to do a different set of parentheses that cause us to do them left to right, which is to say 2, 2, 2, 2, caret, caret, caret. And now I want to cause us to do them left to right. So that means that I'll parenthesize these. And then I'll parenthesize this. And that's going to cause us to do that one, and then that one, and then that one. Okay? Fine. So now continuing. This is now a 4. So that would look like this. 4, caret, 2, caret, 2. 4 squared is 16. So this would be 16 caret 2. And then what's that? 256. So what's the answer to the question? And what was the question? Yeah, is up arrow associative? And the answer is no. Because to be associative would mean that it shouldn't matter where I put the parentheses. But evidently it does. Because 65,000 is not the same as 256. So even though, so addition is associative. Multiplication is repeated addition, and it turns out that multiplication is associative. That's neat. And then we have caret is repeated multiplication, so that's neat. And up arrow is repeated caret, but we lose associativity. You can keep going, right? And then you might wonder, like, how does it change, right? You have plus, and then a dot, and then a that, and then an up arrow, and then, you know, what? And what do I draw next? Like a giraffe? I don't know. But it turns out that you just, to do the next one, so repeated up arrow is 2 up arrows. You just write 2 of them, right, side by side. And then if you wanted to do, that, you know, you could call that double up arrow. There's a lot of ways to say it. You know, repeated double up arrow is triple up arrow, right? You write 3 of them. Okay, and it just goes on, you know, and then there's other ways to do it, but I'm not going to take it any further. So the consequence of this is that therefore this is not associative. But now I have a question, a separate question. If you type, so at the MATLAB prompt, so if you ask MATLAB, if at the MATLAB command line you in fact type 2 caret 2 caret 2 caret 2, if you type that, what will MATLAB write? Will it be that one? Will it be that one? Will it be something else? Will MATLAB complain? What will it do? Which one will it be? And why? Always left to right. Okay, good. So here's a. Did I talk about the order of operations in this class, like on the first day? Not really. Okay. So here's the thing. You might be in for the following circumstance. Is that you know, I'm a math person, and you know, most people aren't. And that means that in a family, usually there's just one. So like you're the one, probably. Have fun with that. So you know, I get sent all kinds of nonsense. You know, they're just trying to like just aggravate me. And here's one. Here's a good one. So if you here's one. So this, and then I'll put a 4 here, and then this. I'll put a 2, and then I'll say add 7, like this. Okay, so then the order of operations that you learned in Miss Harris's class in 4th grade, you know, it's called, you know, she said PIMDOS, right? She was lying, or she was mistaken. I don't know, but it's not PIMDOS actually. The order of operations, you know, PEMDAS, meaning parentheses, exponents, multiply, divide, add, subtract, where multiply means caret. Okay, so then there's 3 operations. Listed, and there's 4 items: 60, 4, 2, and 7. Labeling this is a divide, and this one is a multiply, and this one is an add. Now, if the order of operations is PIMDOS, if it were the case, then which one of those would you have to do first? You'd have to do that first. If the order of operations were PIMDOS. It is not. Rather, the order of operations is really that if there are any parentheses, you must do that first. If there are any carets, supposing there are no parentheses, then you must do all carets first. Supposing there are no carets, you collect all of the multiplies and the divides. They're on the same level. And if there's more than one, well, if there's more than one parentheses, more than one group, you process the leftmost group first. Okay. If there's more than one caret, you process the leftmost caret first. If there's more than one multiply or divide, you process the leftmost one of those first. And then A and S are on the same level also. So now, concerning these, you know, you can consider this like level 0, level 1, level 2, level 3, and you must do the ones nearest the top first. So notice that A is below that, but D and M are on the same level. So they're tied, you know, for levelness. So how do you choose? How do you break the tie? Leftmost. That breaks the tie. So in fact, the order of operations is saying that you have to do that first. So ties are broken left to right. So then the correct answer is that this would be 15, because you have to do that first, and then multiply 2 and then add 7. And then now that's a multiply, and that's an add. So the multiply wins. So that this would be 30, and then add 7. And then this is an add. And of all the operations, which one wins? The only one, right? So this would be 37. You know, you might say, I don't know. I was listening to this guy first, but then after he's, you know, bad talking Miss Harris, I really trusted Miss Harris. I loved her. You know, she was my 4th grade teacher. I think this guy maybe not have it right. So then here's you know, we could just say, you know, maybe TI, you know, can be the arbiter of truth. So there I have it typed. And if the order of operations is really the other way, that you should have done that first, then it would be 60 over 8, which is something. I don't know what it is, but you won't get 37. Okay? So that being the case, if you ask MATLAB to do this, what will you get? You'll get 256. Because what MATLAB does is it analyzes this expression, and it says, here's an E, here's an E, here's an E. Those are all tied, and therefore the tie, I only do one thing at a time, so I have to break the tie. How is the tie broken? Left to right. Okay, so as a result, MATLAB will say that. Good. And continuing that remark a little bit, I'll take the time to tell you that y'all have taken or will soon take calculus. In your calculus course, you should never ever write this. Why not? The reason is because it's a bit confusing. Is that if you're in a calculus class, and you see a question that says that, it almost surely means this. It almost surely means exponential of x squared. That's probably what it really means. But according to the order of operations, that actually means exponential of x squared. So beware. Any question about this? Good. So next thing. Let's see. I talked about. Oh yeah. So when I brought up this add thingy, the way that I brought it about is I just sort of I just sort of said, like, here's factorial, a thing you know, and look, it's all multiplies, and then more or less on a whim and for fun, I said, let's change it all to add, and then we just came up with that. Okay, this new thing. Now that's that's neat, but it's pretty abstract. Okay, and then I said, we didn't write another function, but you can imagine that I could say, okay, now do exactly this one, but with up arrow. Right? But that's pretty dry. Another thing about teaching is you should always sort of give a good reason for the reason why you're doing things. Okay, why are we talking about this at all? So one of the ideas in math is that you kind of want to take a theorem or something and you kind of want to boil it down to its simplest thing. So it's like completely abstract. But the problem with that is that when you see a new proof or something like that, the author might have completely omitted why were they thinking about that in the first place. And a particularly bad example in history, or good example, I guess, someone who did that quite frequently, is a mathematician you've surely heard of named Gauss. Okay, so he's like super mathematician. Right, and other things, but at any rate, he's held in high esteem among mathematicians. So, and another good important thing about teaching is that you kind of need to insert some culture, so that you can have some frame of reference. Like, why are we talking about this kind of thing? So here's a story about Gauss. Okay, his story. It's probably entirely lies, honestly, but maybe it's true. Maybe it's maybe part of it is true. So in real life, Gauss proved a lot of math theorems. And all of his contemporaries and the people that came after him kind of like had a love-hate relationship with him because he really came up with some really great results. But the way he published them were like, why did you even think of that? Where did that even come from? And he would refuse. Like people would say, what led you to that? And he would say, no. I won't won't tell you. So he's kind of a jerk, and he was a jerk even when he was a kid, at least according to this story. So here's the idea: you got Gauss. He's a young person, like 8 or whatever, and he's at school, and he's already very, very difficult to be around person, and he's smart, so he doesn't really need to listen to the teacher much, and he's aggravating the teacher, and the teacher says, "Okay, look, I need you to be busy, okay." So this is what I want from you, Mr. Gauss. I want you to add up the numbers 1 through 100. I want you to do 1 plus 2 plus 3 plus 4 all the way to 100, and I want you to do it. And don't come back to me until you've done that. And he looks right at Mrs. Harris and says, 5,050. And then after, about 10 minutes of checking, Mrs. Harris sees that he has the right answer, and continues to pull her hair out. Okay, fine. So how did Mr. Gauss do that? So here's the idea: is that notice in the apocryphal story that's probably not true. In the end, the question was that Mrs. Harris said, do 1 plus 2 plus 3 plus all the way up to 100, right? But I'm going to go ahead and put the 0 there. She didn't say that. Or she through I through me didn't say that, whatever. So then now we're going to go all the way to 100. And so 97, 98, 99, 100. So that was the request that was put to the young Mr. Gauss. And notice that would be a of 100, right? That a function that we wrote on the first page. That'd be a of 100, but with the terms in the reversed. So, the apocryphal story continues and says, well, how did he do it? So who knows the secret? Yeah?
I mean, you take the two end terms,
Uh-huh.
add them together, and just keep on going inwards, basically, and they all add to 100. So.
Very good. So consider the first and last. So if you add those two together, how much is that? That's 100. And now, conceptually delete them from the list. And now the new first and last is that if you add them, what do you get? 100. The new first and last, you add them, you get 100. The new first and last, you add them, you get 100. So you can see that we can keep pulling out 100. And then the question is, you can see that we can keep doing that, but then a question arises, how many times can you do that? What would be the last pair you could extract? 49 and 51, right? So that would mean so we're able to go all the way to 49 and 51. How many pairs is that? That's 50 pairs. Okay, 50 pairs. And then, because 49 and 51 are the last pair you're able to extract, there's one left in the middle. And what's that? 50 is left in the middle. So as a result, the answer to the question is that we're able to get 100. The number of times we're able to do that is 50 times. And then after we've done that 50 times, there's one left in the middle, and that's 50. And of course, that's 5,050. Okay, that's neat. Now, generally, the pattern kind of looks like this: 0 plus 1 plus 2 plus ... plus n minus 2 plus n minus 1 plus n, like that. So now we're able to extract n, right? So n, etc. Now I need to make a slight modification here, or clarification. I need to say let n in the naturals be even. Because strictly speaking, if I'm going to make the same case that I did there, to have one left over in the middle, that argument, then the same way that 100 is even, this must be even. So doing that, we're able to take n. How many times are we able to take n? N over 2 times. And then when we've done that, there's one left in the middle, and what is it? N over 2. All right. And then, if you factor out the common factor and algebraic simplify and all that, then you get this. Incredible. So that's what happens for even n. And the argument that I've put forth is a little bit sloppy and definitely does not apply to odd n. Nevertheless, this is the formula for n's that are odd and for n's that are even. It works for both. And I leave it to you to sort of think about why that should be the case. So that's interesting. So what I want you to observe is that besides that formula, that function formula that we wrote for A, where you had to, all the parentheses, besides that, it is also the case that you could express A like this. Now, if we wanted to evaluate A of 100 using that formula, this one right here, then we'd have to do basically around 100 steps, right? We'd have to actually do 0 plus 1 plus 2 all the way. That's what Mrs. Harris wanted Gauss to do, right? But if we use this, this is like maybe 3 or 4 steps, right? You take the n, you add 1, you multiply it by the original n, and then you divide all that by 2. So that's like 3 or 4 steps. So this is far preferable to that one, as far as, well, it's preferable if you're the one computing it, right? Mrs. Harris would have preferred that Mr. Gauss use this one. Okay, but does everybody see the distinction? So this is the case if you're doing adding. Now that to me raises the question that well, if this is the repeated multiply function, which is to say the factorial function, and if you switcheroo things from multiply to add, then you can have this nice formula. Should it be the case that there's a nice formula for factorial? Because if I asked you to do 100 factorial, then right now you'd have to do basically 100 things, right? You have to do 100 times 99 times 98 all the way down the line. And my question is that how about it? Is there a formula analogous to this for factorial? Is there one? So if we made it like a democracy, if math could be a democracy, then the no's would have it in the sense that you're not aware of one probably. And then you might think, okay, well, if not very many people are aware of it, maybe it doesn't exist. Of course, math isn't a democracy, right? It isn't. But nevertheless, the answer more or less basically is no. There is not a formula analogous to this for factorial. There isn't one. And that's a curious thing, isn't it? Why should there be one if it's repeated add, but not if there's repeated multiply? If you want to look more into that, so the question I'm raising here is, what about factorial? Can you do something like that? And more or less the answer is no. But if you want to read more, you can read about something called Stirling's formula. Good. Now again, if this wasn't concrete enough, giving an apocryphal story about Gauss, now I'm gonna do something that at first seems completely may seem completely out of the blue. So you know what a cannonball is? Like the thing that people shoot at each other. The metal thing. And like this historical documentary was that had Johnny Depp in it. Where he's like a pirate. You know what I'm talking about. Can you imagine how difficult it would be if there's like hundreds of those cannonballs all over the deck? When it's all the waves and stuff. So you want to be able to like stack them so that they'll be stable, and won't move around. So can you imagine the problem of stacking cannonballs? Good. So you can imagine Johnny Depp doing his thing with the cannonballs, stacking them. Fine, but now I'm going to say that actually we're going to use two-dimensional cannonballs because I want to draw something. Now you can and we will do the same problem with three-dimensional cannonballs, but we're going to do two-dimensional cannonballs for now. And the question is that if we want to make a little stack, that's shaped like a pyramid of cannonballs, the question is, how many levels? We want to consider the number of levels. How high are they stacked? If we had one cannonball, how could we make a stable configuration of one cannonball that's one height? And you can do it like this, right? Assuming you have like little things right there that sort of keep it from rolling side to side. So they're like it's stuck there now. So that's a pile of that's 1 high. So now if you wanted to make a pile that was 2 high, I don't mean necessarily 2 cannonballs, I just mean that it's 2 high. There's 2 levels. How many cannonballs would it take to be stable? It would take 3, right? Because you couldn't get 2 cannonballs stacked right on top of each other. That wouldn't be stable. Just the slightest little nudge would, it would topple. So what I'm saying is that, if you had 2 cannonballs for the bottom there, if you had 2 of them and they were, side by side like that, so that they were touching, then you could get another one on top. And that being height 2, that would be a stable configuration. Again, assuming you have like little block thingies there that keep those from going side to side. Okay, so this is the if you want the height to be 1, that's the stable configuration, and if you want the height to be 2, that's a stable configuration. What about the height 3? How many cannonballs would we need? 6. Now why 6? Yeah, because you need 3 on the bottom, right? So if we put 3 on the bottom now, if we do that, then because there's little things here that keep those from rolling side to side, and then here on top of that we could put 2 there, and then on top of that one we could put 1 there. So that'd be stable. Okay, so if this isn't forced enough, then I'll do 1 more. So what if I wanted to make one that's height 4? How many? Need 10. Now why 10? Okay, good. So I could, if we had 4 on the bottom now, if it was 4, then on top of those 4, it'd be possible to put 3. And then on top of those 3, it'd be possible to put 2. And then on top of those 2, it'd be possible to put 1. So this is the in is 4's case. Now, what about if you wanted a pile of cannonballs that had height 0? How many cannonballs would be required for it to be stable? 0, right? So there's the n equals 0 case, right there. So now, how many cannonballs are required here? So I think I heard y'all say that this is 1. 1 is required for this. 0 are required for that. 3 for this one. And then to get this one, well, do you observe that if this is 3 there, well, isn't that 3 right there? So really it's got to be that much more plus the 3 that I needed there. So this should be 6. Similarly, do you observe that here's a pyramid of height 3 right there, and so that pyramid, that stack right there, is really that whole thing, And so this pyramid of height 4 is really sort of like a base on the bottom, and then on top is a pyramid of height 3. Okay, and I think you can imagine going that way. Similarly, we could take this pyramid and say that's that one. Okay, and so here's 10. But at any rate, can you see that the stable configuration, if you just wanted to count them up and not realize that relationship there, it would be 4 plus 3 plus 2 plus 1? Is it too forced? This is exactly the same thing as the A function, isn't it? The number of cannonballs. Okay, as a result, the A function that we wrote on the first page is very often referred to as the pyramid function, because it tells you how many, well, I guess better would be to say the two-dimensional pyramid function. How many cannonballs, two-dimensional cannonballs, do you need to make a stable pyramid of height n? So these are referred to as the pyramidal numbers. Pyramidal numbers. All right, good. Now, I'll just mention it and then move on, is that this is the two-dimensional case. If we had disks. If you imagine the three-dimensional case, what it's going to be now is that instead of the bases being shaped thus, like that, and then that, and then that. What they're going to be is, in your mind's eye, imagine a square, like a sandbox that's square. Okay, and its size is such that you can get 3 by 3 cannonballs in it. Yeah, 3 by 3. And then on top of those, you'd be able to put more cannonballs. In fact, a square amount of cannonballs. How many would you be able to get on top of 3 by 3? 2 by 2, 4. And then on top of 2 by 2, 1. So instead of being 1 plus 2 plus 3 plus 4 plus 5 like that, it'd be 1 squared plus 2 squared plus 3 squared plus 4 squared, etc. Okay, so I'll just leave that. I'll leave that in the air for you to think about. Any questions so far? All right. Finally, the last thing I want to mention is that do you remember when we did the Fibonacci thing, and I wrote down the Fibonacci definition, and then I did that just terrible, just a train wreck of a calculation? Do you remember it? Okay, good. So the definition that we wrote was this. It was this. So 0 in the case of the least natural, 1 in the case of 1, and then otherwise the Fibonacci number is the sum of the previous two. And I carefully, as careful as I could, I made that terrible calculation. Okay? But it's manifestly not as fast as can possibly be, surely not. Because the way that you do it, like you can teach this to grade school kids eventually. You can say, well, let's compute the Fibonacci numbers. The first two are 0 and 1. And the next one is always the sum of the two that you know. So what's the sum of 0 and 1? 1. So now you can forget the last one. So now you can forget 0, now you have 1 and 1. What's the next Fibonacci number? 2. So now you have 3 numbers, 2, 1, and 1. You can forget the first one. So now you have 2 and 1. What's the next one? 3. So now you can forget the last one. Now you have 3 and 2. The next one is 5. You can forget the last one. Now you have 3 and 5, and the next one's 8. Right? So you just need to know 2, and then you just sort of repeatedly forget the oldest one. This kind of definition can't possibly do that. It can't possibly calculate in that way. And the reason why, in the end, it can't calculate that way is because every time we do this, we only know one thing. We only know n. We don't know how far we've made it. We don't know 2 things. We just have this n. So to make this work better is consider the following. So I'll define 2 functions. In fact, I'll define g. The only reason why I'm saying g is that's the next letter after f. That's the only reason. And the only reason why I'm using f is for Fibonacci. Okay. So I'm going to define g, just like f is naturals to naturals. I'm going to define g naturals to naturals, and it is going to be the Fibonacci function. It's going to do it, but it's going to do it in the clever way, the better way, where you know 2 and then you get the next one. But in order to make that happen, in fact, I need to define 2 functions. So I'll do g, which is supposed to do the same thing, which is supposed to calculate the same result as f. But in addition to that, I'll make a g and then a party hat, whose signature is going to be naturals, cross naturals, cross naturals, 2 naturals. So now the existence, the purpose, is you can think that, well, this g is like a function that has 1 input and produces 1 output, but this g with party hat has 2 more inputs. It's got 2 more. Though the purpose, for that one and that one, the purpose of those 2 is that's the 2 that you're remembering. Okay? So we'll define it like this. So g of n is going to be g party hat of n, And then in these positions, in the second and third, or in that slot and that slot, we're going to write the first two Fibonacci numbers. So what are the first two? 0 and 1. So the reason why 0 and 1 in the end is because those are the first two. If the first two Fibonacci numbers were something else, then you'd write whatever that is. So that's nice, but that's entirely not helpful unless we also know what G party hat is, right? We got to know that. Otherwise we can't proceed. Okay. So G party hat N, and then I'll write A0, A1. Now those are just names, so that we can refer to that one and that one. It will be defined like this. So it will be two clauses. One of the clauses will be when n is 0, and then there will be an otherwise. Now suspend belief for a moment and imagine that I asked you to evaluate g of 0, so that n is a 0. Now according to your prior knowledge, you know that Fibonacci of 0 should be what? 0. And if n is 0, then there's a 0. So for reasons that aren't entirely clear yet, I'm going to say that the answer should be A0. Okay, it's not entirely clear why I'm saying that, but bear with me. So that's going to signify that, in a sense, we have no more work to do. We've arrived. This one is going to mean that there's more work to do. We haven't arrived yet. So we're going to recurse to G party hat to 3 arguments here. So again, the A0 and A1, those represent the things that you know. So like, for example, if we were at the place where it said, 3 and 5, what's the next one? 8, right? So if you know 3 and 5, if you know those two, then you're able to find the next one. So what's the formula that goes right there? Not 8. What's the formula in terms of these inputs? It's the sum of those two, right? Those are the two that you know. So A0 plus A1. That's what goes right there. Now what goes right there? So the big one is there, but the old big one is the new small one. So what goes right there? A1. And then supposing you do that, you, in a sense, have done one step of work. So the new first argument will be what? N minus 1, to help us record that we did one, in a sense, one item of work. So now, in the time remaining, I'm going to evaluate so that you can see. So if we do G of, say, 7, according to the definition, this would be G party hat 7, 0, 1. Always 0, 1 to begin with. Then we're going to use the second clause repeatedly until we hit the first clause. So this would be G party hat. The first argument would be 6. And now this argument transitions over to that location, 1. And then the new argument is the sum of those two, 1. Then it would be G party hat of 5. This argument transitions, moves 1 position to the left. That's a 1. The new argument is the sum of those two, which is 2. So now, in interest of time, I'll just race to the end. So this would be 5, 2, 3, 4, 3, 5, 3, 5, 8, 2, 8, 13. Did I make an error? Oh, look at what I did. Okay, wait a second. I'm glad Joe caught me. So 7, 6, 5, 4, 3, 2, 1. Now did I do it right? 2, 3, 3, 5, 5, 8, 8, 13. Yeah, good. So now G 0, 13, 21. And now finally, that that first argument is 0, that means that, that we have no more work to do. Essentially, what this thing counting down is saying, it's saying like, how much further do you need to go? So we don't need to go any further. So we're in the first clause. So what's the answer? So the arguments are how much further you have to go, the small number and the big number. So what's the answer? 13. And if you look carefully at the notes from the first day, the answer was 13. Ah, this is much better, isn't it? Okay, good. So that gives us something to think about. But there's a way to do this even faster, and we'll talk about that a little later. So have a nice Thursday.